So this video is a quiz video which gives you an opportunity to practice integration by parts. And we have here 5 exercises, and the idea is that you should write them down and then try to solve them on paper one by one. Having done that, you can look at the next slide in this video where I will post the answers to each one of the integrals in turn, and that way you can check whether you have got them right or not. After that, on the following slides, I will go through the detailed answers to each of these videos in turn in case you'd like to see the details. So with that, I suggest that you pause the video and go through the problems. Welcome back. I'm now going to go on to the next slide. So on this slide I've written out the answers to the integrals, and this integral here, through a single use of integration by parts, gives us this result, which is easy to check by differentiation, and it should indeed be checked by differentiation. They all should. The second integral is a classic example of the use of integration by parts. We write the integrand as 1 times itself, and the reason we do that is we don't initially know how to integrate this function, but we do know how to differentiate it. So if we write it as 1 times itself, integrate the 1, differentiate the log, we have the hope of getting this integral to work, and indeed it does. The second integral requires 2 uses of integration by parts. The third integral requires a use of integration by parts, some trigonometric identities, and solving an equation, a simple equation for the integral. And the final one, in a similar way to the case of the logarithm, requires knowing the derivative of arcsine and writing the integrand as 1 times itself and then using integration by parts. So if you have not been able to get the answer to any of these, the detailed answers follow on the next slides, integral by integral. So when we look at this integral, we cannot immediately see what the answer is, but we recognize that there is a product here, and we think it might be worth trying integration by parts. And the first question when you're going to use the technique of integration by parts is, what are you going to choose to integrate and what are you going to choose to differentiate? And I think it is often very helpful to remember the word late, and this stands for logs, algebra, trigonometry, and then exponentials. And we look at the factors here. This is an algebraic factor, and this factor here is a logarithm. And what we do with the idea of late is the factor that appears first in this word is the factor that we differentiate. It's worth exploring, trying to do it the other way around, and seeing that that makes life harder. So let's have a go at this, and what we're going to do is we're going to choose that u, the factor we're going to differentiate, is the logarithm of x. So the derivative of u is 1 over x, and that means the other factor which we're going to integrate, which I'm calling v prime, is x cubed, and v is its integral, and that is x to the 4th over 4. And now let's recall the integration by parts formula. And that tells us that the integral of u times v prime with respect to our variable is u times v minus the integral of u prime v with respect to our variable. So what it's telling us is that we have an integral and it's equal to something minus a different integral where we've swapped around which factor is being differentiated. And this of course follows from the product rule. So let's now do our integral. It tells us that I is u times v. U is here, v is here, so I is x to the 4th over 4 times the logarithm of x, because I think it's more attractive, better to read. I've written the algebra in front of the log. And then we subtract the integral of u prime, which is 1 over x, times v, which is x to the 4th over 4 with respect to x. And now we see a simple cancellation. The 1 over x cancels with the power of x to the 4th and turns it into x cubed. So therefore we can carry out the integral that is left here quite easily, and we have that I is x to the 4th over 4 times the logarithm of x minus, and now what we have here is the integral of x cubed divided by 4. The integral of x cubed is x to the 3 plus 1, x to the 4, divided by our new power 4. There are two factors of 4 on the bottom, this one and the one that comes from integrating the x cubed. So we get overall minus x to the 4th over 16 plus an integration constant. And that is our final result, and it may be checked by differentiation. And if you differentiate this, you will obtain x cubed times the logarithm of x, our initial integrand, and that will tell you that this is the correct result for the integral. So with that we can move on to the next integral. So our second integral, the first time somebody encounters this, may look a little bit unusual because there's perhaps not obviously a product. But anything can always be written as 1 times itself. And now we have a product. And our word late indicates that it may be useful to use this factor here as the factor which we are going to differentiate, and this factor of 1 as the factor that we are going to integrate. So recalling our key formula, that the integral of uv prime with respect to our variable here x is uv minus the integral of u prime v with respect to x. We have u is the logarithm of x, so u prime is its derivative, and that is 1 over x. V prime is 1, so v is the integral of 1, and that is x. So therefore our integral, the logarithm of x with respect to x, is from our formula u times v, so x times the logarithm of x, so that is x log x, minus, because of the sign here, the integral of u prime, but u prime is 1 over x, times v, and v is x, integrated with respect to x. And now we see the cancellation that the x on the bottom and the x on the top cancel, so we are left with the integral of 1, and that is just going to be x. So we obtain that the integral of the logarithm of x with respect to x is x log x minus the integral of 1, which is x, and then there's some unknown integration constant. And again, strongly encourage, check this result by differentiation. And using the product rule here, not forgetting that term, you should obtain the logarithm of x, the original integrand. So with that, we'll move on to the third integral. So again, this is not a trivial integral. We don't look at it and spot the answer, but we do see that there are two possible terms in here, the natural ones, x squared and e to the minus x. So we think to ourselves, let's try to use integration by parts. And again, from the word late, if you remember late, algebra is before exponential. So therefore we decide that this is the term that we are going to associate with u, this is the term we are going to differentiate. So that is u and this is v prime. So u is x squared, u prime is 2x, v prime is e to the minus x, so v is its integral, it is minus e to the minus x. When we differentiate this, we get back e to the minus x. The minus sign comes down here to make a plus sign. So from our integration by parts formula, the integral of u v prime dx is uv minus the integral of u prime v with respect to x. We have I, our integral, is u times v, that's x squared times minus e to the minus x. So that's minus x squared e to the minus x minus the integral. And now there is going to be a factor of v again, and that has a minus sign in front of it. So I'll immediately make this here plus. There's a minus sign from the integration by parts formula, and there is another minus sign from here, so the two give us a plus sign. And now we have a factor of 2x from u prime, and we are left with an e to the minus x from the v factor. And we look at this and think we could use integration by parts on this again. If we compare this integral with this one, it's clear that using integration by parts has reduced the power of x squared to a power of x to the 1. And if we use integration by parts again, we can hope that the x is going to be replaced by an x to the naught. X to the naught is constant, and that will give us an integral of e to the minus x, which is a standard integral. So let's look here, and let's say that this factor here, e to the minus x, is again v prime, and x here, I'll pull the 2 outside of the integral in a moment, x is going to be the u factor. So u is x, u prime is 1, v prime is e to the minus x, v is therefore minus e to the minus x. If I differentiate that, I get back to that, and 1 is the derivative of x. So again, using the integration by parts formula here, we obtain I is, let's not forget this term that was here, so it is minus x squared e to the minus x plus, and I'm going to open brackets, we're going to have all the terms now from here. So we have a factor of 2 here multiplying everything, and I'm going to pull that out so I can actually pull the 2 out in front of the brackets. So let's put this large 2 here. And now we have u times v, u is x, v is minus e to the minus x, so I'm just going to put the minus sign in front and an e to the minus x. Then we have minus the integral, and now we have u prime, which is 1, times v, and v is now minus e to the minus x, so I'm going to again change the sign here. So there are 2 minus signs, one from the integration by parts formula, one from here, and then we are left with an e to the minus x dx. Close the big brackets, and this integral is a standard integral, the integral of e to the minus x. So therefore we have that I is minus x squared e to the minus x minus 2x e to the minus x. So I'm opening the brackets here and remembering to multiply everything by 2. And then we have plus 2, but I won't write the sign down immediately because the integral of e to the minus x is minus e to the minus x. So e to the minus x, and there is an extra minus sign from that integral, so that I put here, plus an integration constant from this last integral. And that's our answer, but we can tidy it up a little bit in a way that for a differentiation check makes life a lot easier. So I'm going to say that therefore we conclude that I is, now we look at that, minus, 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 that's an overall factor, and e to the minus x is as well. So it is minus e to the minus x, brackets, x squared plus 2x plus 2, close brackets, plus our unknown integration constant. That is our result, and again, I would encourage you to check it by differentiating. So, in this example, we used integration by parts, and we had to use it twice. And one of the key things to notice when you do this is if you have a term like this 2x that you had gained by differentiating something, this was obtained through a derivative, in the next step you have to differentiate it again. Otherwise you just go backwards and you would end up with the fact that this integral is equal to the integral of x squared e to the minus x, which is clearly true and clearly useless. So if you differentiate one factor and integrate the other factor, and on the next step you want to use integration by parts again, don't swap things around. If you do, you just undo all of your work. Okay, so with that, let's go on to the next slide. So in this next integral, we want to integrate the cube of the secant function. And I think the key thing that we recognize that helps us to do this is that even if we don't know how to integrate the cube of the secant function, we do know how to integrate the square of it, because the square of the secant function is the tangent function, because if we differentiate tangent, we get the square of the secant. So that means that in our integral here, we can divide up the integrand and say that our integral is sec theta times sec squared theta. And now we have been able to divide our integrand into two factors, one of which is easy to integrate. So this factor here we are going to call v prime, and this factor here we are going to call u. So u is sec theta, so that means that its derivative, u prime, is sec theta times tan theta, which we can obtain, if you wish, by saying sec theta is 1 over cos and use the chain rule for powers, or we can just remember that the derivative of sec theta is sec theta tan theta. And we also have that v prime is sec squared theta and v is tan theta. So from our integration by parts formula, the integral of u prime times v with respect to theta, our variable now, is uv minus the integral, and we swap it around, it's the derivative of v now with respect to theta. We have that our integral I is u times v, and u is sec theta, v is tan theta, So it is sec theta tan theta minus the integral of, and now it is u prime, which is sec theta tan theta, multiplied by v, and v is tan theta, so we put in an extra factor of tan theta, but tan theta times tan theta is just tan squared theta, all integrated with respect to theta. So it might for a moment look as though our integrand, the new one, is actually worse than the initial integrand, but there is a very useful identity that we should now recall, and that identity is that we can write sec squared theta is tan squared theta plus 1. And this identity is actually just the identity that 1 is sine squared plus cos squared, and then we divide everything through by cos squared theta, so the 1 over cos squared theta is sec squared theta, etc., etc. So from this we see that therefore we can write tan squared theta, which is the factor in our integral above, or one of the factors, is sec squared theta minus 1. So this means that our integral I is sec theta tan theta minus the integral, and then we have sec of theta times tan squared theta, so that's open brackets sec squared theta minus 1, all integrated with respect to theta. And what we have done now is we've turned this integral here into actually a difference of two integrals. One is the integral of sec theta times sec squared theta, and that is therefore sec cubed theta, and that is our initial integral, minus the integral of sec theta times 1, so just the integral of sec theta. So this means that I is sec theta tan theta minus the integral of sec cubed theta, and now it's minus minus, so therefore overall, d theta is missing, plus, and now it's the integral of sec theta with respect to theta. This integral here is just our initial integrand, I. So what I'm going to do now is I'm going to take it over to here, because what we have is now an equation with our unknown integral here, our unknown integral here, this algebraic term, this product of two trigonometric functions, and here an integral, but that's a standard integral that we recognize. So taking this over to here is going to give us twice our initial unknown integral is equal to sec theta tan theta plus, and now the integral of the second function is the logarithm of the secant of theta plus the tangent of theta, and now I'm going to write an integration constant, because otherwise on this side there would be no hint of the ambiguity which is present here. And now all we have to do is divide both sides by 2, and we obtain that the integral I, the integral of sec cubed theta, is equal to 1/2 sec theta tan theta plus 1/2 logarithm sec theta plus tan of theta plus an integration constant. And that is our result for the integral of sec cubed theta. And again, we can and should check it by differentiation. So this is a little bit different to the previous cases. As well as using some trigonometric identities, recalling this result and this result here, the key difference is that after we used integration by parts, we obtained the initial integral again here, and we had to bring it over to the other side, giving us twice the initial integral here. So with that, I'm going to stop this and move on the next slide to the final integral. So in this integral, the integral of arc sine of phi with respect to phi, we may not recall immediately what the answer is. I certainly don't myself. But if we know how to differentiate this function, then integrating it using integration by parts is not too difficult. So what we do is we write this as the integral of 1 times arc sine of phi with respect to phi. This is just like the logarithm, so a function that you know how to differentiate, you can write it as 1 times itself, use integration by parts, and see if that works. So here, this is what I'm going to integrate, and this is what I'm going to differentiate. So this is u, and this is v prime. So u is arc sine of phi, and the derivative of arc sine is 1 over the square root of 1 minus phi squared. And if we know this result, we can calculate this integral. So now, the other factor, v prime, is 1, and the integral of that is just phi. So from our integration by parts formula, that u v prime integrated with respect to phi is u times v minus the integral of u prime times v integrated with respect to phi, we have that I is u times v, so that's arc sine of phi times phi. I'll put the phi in front, so it's phi arc sine of phi minus the integral of phi times, and now it's the derivative of arc sine, and the derivative of arc sine is this, so that's 1 over the square root of 1 minus phi squared with respect to phi. And this integral here is actually not too bad. It's one we can do by inspection. So if we look at this, you recognize that up to numbers, this is the derivative of 1 minus phi squared. This factor is 1 minus phi squared all to the minus a half. So you could imagine that if you differentiate 1 minus phi squared to the plus a half, so ignore that for the moment, then if you differentiate it, you could easily get this integrand up to numbers. So let's just try it. I is going to be phi arc sine of phi minus, I'll just leave that for the moment, the sign, not worry too much. And now I'm going to say it's the square root of 1 minus phi squared plus an integration constant. And now let's just look at this and see what happens when we differentiate it. If I differentiate that, this is 1 minus phi squared all to the half. I'm going to bring a factor of a half down. I'm then going to reduce the power of this from plus a half to a half minus 1, so minus a half. And that's exactly what I want from here. And I'm then, using the chain rule, going to be multiplying by the derivative of 1 minus phi squared. And that is 0 minus 2 phi. The 2 and the half that we had from this power here are going to cancel, and there will be a minus sign. Now, if I had a minus sign here, minus minus would give plus, and I want minus. So I will make that plus. And now again, if we think about it, if we differentiate this, we will obtain minus phi over 1 root 1 minus phi squared. So this is correct. So to perform that integral by inspection, you can perform it by substitution, with your new variable in the substitution being 1 minus phi squared. But if we can do it this way by inspection, I think it's more efficient. As far as integration by parts is concerned, the key thing in this example was to recognize that if you know the derivative of a function, you can write it as 1 times itself, and in the parts differentiate that and integrate the 1. And with that, I will stop this video.